Before we finish our discussion on solving systems of equations by elimination, there's a couple special cases that we need to take a look at. They produce solutions that are not typical. So let's do that. We've got two right down here that we want to look at. Here's our first special case. So we want to solve this system of equations. Find the xy coordinate point at which they intersect on a graph, which is the solution to that system of equation. To do that, first we need to make sure that the equations are written in the same term order. It looks like that's set for me already. I've got my x's first, then my y's, then my constants. So I'm good there. Okay. Now I need to make sure that I have opposite coefficients on one of my variable pairs. So I look at the x's and I see -2 and 1. Definitely not opposites. I see 8 and -4 in front of the y's. Definitely not opposites. Okay, but I see that if I take this bottom equation here and I multiply that bottom equation by 2, that it's going to turn this -4 into a -8, which will be an opposite of the other 8 in front of the other y, which will give me a pair, a variable pair that has opposite coefficients. So let's go ahead and do that. I've got -2x plus 8y is equal to 8 in the numerator still. But multiplying this 2 in produces 2 times x is 2x. 2 times -4y is -8y. And 2 times -4 is -8. Great. So we now have opposite coefficients in front of the y's. So they're in the same term order, and the y variable pair now has opposite coefficients. So I can add them together. Let's take a look at what happens. Well, -2x plus 2x is 0. 8y plus -8y is 0. You're starting to see why this is a special case. Is equal to 8 plus -8 is 0. Well, the unique thing about this special case problem is both the x and the y were eliminated in the process of elimination. There is no x or y left to solve for. And if we look at what happens, we end up with the equation 0 equals 0. The question is this a true statement? Well, 0 does equal 0, so this is a true statement. Okay. However, it doesn't allow us to solve for the xy coordinate point. Well, there's a reason for that. When we get a situation in which the process of elimination produces a result that is true but not useful, meaning both the x and the y are eliminated at the same time, this means that there is an infinite number of solutions. An infinite number of solutions. What does this look like on a coordinate plane? If this was the graph of one of the equations, the graph of the other equation would lie right on top of that graph. In other words, they're the same exact line. They share every point in common. So they intersect at an infinite number of points, meaning there's an infinite number of solutions to this system of equations. They're the same line. They're just written in a different form so you don't see it. But they are the same line. So if you get a result where it's not useful, meaning the x and the y both eliminate at the same time, but the result is still a true statement, 0 equals 0, that's a true statement, okay, we say that it has an infinite number of solutions because it means that the two equations are the same exact line. One is stacked on top of the other. So that's our first special case. Now let's take a look at our next special case equation, system of equations. Okay, so here we go. We've got 3x minus 3y is equal to 19, and we have 10x minus 10y is equal to 30. Okay, so first things first, are both equations written in standard form so that the x's, y's, and constants line up? And it looks like it is. I've got my x's lined up here, I've got my y's lined up here, and then my constants lined up on the other side of the equal sign. Great. So what I'm going to do next is make sure that I have opposite pairs. Well, 3 and 10, definitely not opposites. Negative 3 and negative 10, definitely not opposites. And just like one of the other problems we worked through, 3 does not go into 10 here or here. So I'm going to have to multiply both equations by something. The way I do that is, well, let me just pick one pair. I'm going to pick the x's. So I need to find the least common multiple of 3 and 10. Now the least common multiple of 3 and 10 we know is 30. So the question now is, how do I turn this 3 into 30, and how do I turn the 10 into 30? Also, you'll notice that both are positives. I want one of them to be negative so that when I add them together, they're opposites and they cancel out. Well, first off, how do I make 3 into 30? Well, I multiply by 10. Secondly, how do I make 10 into 30? Well, I multiply by 3. But I'm going to multiply by negative 3 so that it turns it into a negative 30, therefore opposite pairs on the x's, or opposite coefficients on the x variable pair. So bringing in this 10 times 3x is 30x. 10 times negative 3y is negative 30y, is equal to 19 times 10 is 190. Now bringing in the negative 3 to the bottom, negative 3 times 10x is negative 30x. Negative 3 times negative 10y is positive 30y, is equal to negative 3 times 30 is negative 90. Great. So I now have opposite coefficients on my x's like I intended. So I can add them together now. When I add these two equations together, you're going to see something similar to what already has happened is going to happen again. But it is going to be slightly different. So 30x plus negative 30x is 0. And then you're noticing here that negative 30y plus 30y also produces 0. So both variables again cancel out. And this equals 190 plus negative 90 is 100. Here's where it's different. This equation produces 0 equals 100. Just like the previous example, both variables are eliminated. But does this produce something that is a true statement? No, it doesn't. 0 does not equal 100. This is false. What this means is there is no solution. There is no solution to this system of equations because it produced a statement that is obviously false. Graphically speaking, this means that both of my equations are parallel to each other. In other words, they'll never intersect. There's no point that they share in common. There's no point of intersection. So there is no solution. So these two special cases are the two special cases you'll see with systems of two linear equations. A situation in which there's no solution, meaning the lines are parallel but not on top of each other, and a situation in where there's an infinite number of solutions because the two lines are parallel but one is stacked on top of the other. They're the same equation.